This is Math 251, and we're starting out on section 13.6. We're going to be looking at a couple of applications of our double and triple integrals, specifically the concept of moment and center of mass. We've already seen that it's possible to find the mass itself of an object simply by integrating its density function. If I have a little two-dimensional region, I think of that as what we call a thin lamina. In other words, it's basically two-dimensional, the thickness is negligible. And the density function may be a variable density function, depending on both x and y. Then our mass is just the double integral of the density. Similarly, if I have a three-dimensional solid, d, then my mass is going to be the triple integral of my density function. All right, we're going to now turn from mass to the idea of moment. In one dimension, we've actually looked at moment before. We did it back in Calc 2 just briefly, and you may have seen it in physics as well. The moment is the tendency of a mass to rotate around a fulcrum or fixed point. So if you imagine sort of a seesaw type of a situation, we usually think of x equals 0 as our fulcrum. And then you imagine a mass, I'm just going to call that little m, sitting out here at some other x value. Then the moment, and I'm going to put a little sub x down here, we'll talk about that more in a moment, is just equal to the mass times the distance from the fulcrum. So our mass, little m, times this distance x from the balance point. The reason I put the subscript x here is because as we turn to doing these same things in multiple dimensions, we won't always just have a single axis, like the x-axis or the number line we have here. We may have multiple axes, the x and the y if we're in 2 dimensions, or even the x, y, and z if we're in 3. So the little subscript is just going to indicate which axis I'm working with. Let's then go ahead and turn to the 2-dimensional situation. In 2 dimensions, moment is the tendency of a mass to rotate around a full axis, not just a point. And we typically define 2 standard moments, m sub x, the tendency to rotate around the x-axis, and m sub y, or the tendency to rotate around the y-axis. I've shown you, or I've given you the formulas here, but let's think about those for just a moment. If I have this 2-dimensional region, this is my region R, my thin lamina, and let's suppose that I'm wanting to talk about the moment with respect to the x-axis. If the density here is variable, and certainly the distance of various points from that x-axis varies as well, I can't do this all as one simple algebraic calculation. Instead, I have to think of little pieces of the area. A little area dA. And I could imagine calculating the moment of that little chunk around the x-axis. I could then add up the moments, or in other words, integrate, to get all of the little pieces that would make up my region R. So let's think about that little piece for a moment. If that area dA has a density function, delta of x and y, then the mass of that little tiny piece is density times area, or delta of x and y, dA. Now what about distance? Well, if I'm doing my moment at the right now with respect to the x-axis, I need the distance from that little chunk to the x-axis. So this is my distance. Notice that I've got some random point xy inside my little dA here. Then the distance is really just the y value. So if I want to do my moment with respect to the x-axis, just like I did way back in the one-dimensional case, moment is mass times distance. That's going to be this mass, delta of x and y dA, times the distance, y. Actually, I should probably call that delta of the moment. It's just a little piece of the moment, because again, I would have infinitely many little pieces inside my region that I would have to add up. So to get the full moment with respect to x, I would need to integrate this. Since I have a dA, I know it would have to be a double integral. That's also the only way I can represent my full region R. And then I'm just going to integrate this function. I'll rearrange. I'm going to put the y first, times the delta of x and y, times the dA. And there's that m sub x formula that I was giving you up here. But you can kind of see where the pieces come from. Notice that the m sub y formula is exactly the same with the exception of instead of a multiplier of y, we have a multiplier of x. And if you think about this little piece of area again, the distance to the y-axis would be an x distance. And so everything else stays the same except the distance would become x instead of y. And that's how we would get that formula. We can also do mass and moment in 3 dimensions. In that case, the moments are the moments about each coordinate plane. And again, I won't try to derive all of these. I think if we do one of them, you'll be able to see where they come from. Let's think for a second about the moment about the xy plane. If I imagine that I've got some solid D, there's my D, and within that solid, I've got a little chunk of volume somewhere. We'll say that has volume dV, or delta V. Doesn't really matter. I'm going to change my deltas to D's anyway, in the long run. That little chunk of volume has density function delta of x, y, and z. And so the mass of that little chunk would be the volume times the density. So I'm going to abbreviate my delta as just a delta since I'm running out of space, times dV. If I want the moment about the xy plane, I need to think about some arbitrary point inside that little chunk of volume. Again, we're going to shrink it infinitesimally small, so it'll shrink down to 1 point anyway. And think about the distance from that point down here to the xy plane. That's going to be a height or a z value. So z is going to be our distance. So the moment about the xy plane is the mass of that little chunk times its distance to the xy plane. Or in other words, we would have the distance c multiplied by the mass delta. I'm going to put the fact that delta is a variable density back in, dV. And then I would add up or integrate over all of the little pieces that make up that d. So in this case, I'll need a triple integral since I'm integrating over a solid dV. And there's that. Once again, the only difference to get the other ones is the multiplier, the y or the x. If I were going to go to the xz plane, then my distance here would be a y distance. And the hardest one to draw actually is the one that goes backwards towards the YZ plane. It kind of goes back this way. And that would be an x distance. So you've got the y as the multiplier and the x as a multiplier. All right, the moments in and of themselves probably have uses in physics, but in fact, the biggest use of moments is actually to calculate center of mass of our objects. Think of these as balance points of the object. So if I imagine a two-dimensional region again, the center of mass, x bar, y bar, is just the point that I would have to support that region at in order to get it balanced perfectly. If you imagine cutting this out of some material, cardboard or whatever, this is the point that you'd have to just literally put your pencil on, and then you should be able to lift that cardboard in the air and it would balance perfectly. So it's the single point of support, the balance point. X bar, y bar is calculated as the moment divided by the mass. M sub y over m is x bar, and m sub x over m is y bar. Similar idea in 3 dimensions. Here's our center of mass, x bar, y bar, z bar, and you can see the formula in every case. It's moment divided by mass. All right, as you can tell, there are a lot of calculations that go into one center of mass calculation. Technically, we need a mass, and we need 3 separate moments to get a 3-dimensional center of mass. That's 4 calculations. There are a couple of things that we can do to make this easier. First of all, as is mentioned here, very often the symmetry of the object will help us out so we don't have to do nearly as many calculations. The other thing to notice is that whether we're talking about a 2-dimensional region or a 3-dimensional object, once we set up our limits of integration over that region or over that object, the limits of integration won't change, no matter whether we're calculating mass or any of the moments. So we do the limits of integration once, and then we can reuse them numerous times, which helps out a lot as well. All right, come back for the next video, and we will do some examples.